Good morning, everyone.
Hello, everyone, and welcome to Metrologic Group's presentation on improving accuracy and throughput with the Renishaw PH20 and the combination of PH20 and Metrolog X4. So as part of our commitment to safety, our companies and our parent company, Sandvik, we like to always take a moment and pause and talk about safety first. So safety is always important, whether you're listening to a webinar or you're participating in work in an office or as a remote location. Think about things that are relative to your safety, like where you would go in the event of an emergency, where you would assemble, who you would call. Those are the kind of things that we're talking about with safety first. In the event that there's an emergency while you're on this webinar, feel free to jump off the webinar and we'll have it recorded and you can get a copy of a link to the presentation later. So we'll go ahead and make some introductions. Who's going to be on the presentation today? First is myself. My name is Mike Anderson. I'm the North America Reseller Sales Manager for Metrologic Group. Also with me on the call is Alex Clement. He's our Key Account Manager, and Michael Swift, Applications Engineer for Metrologic Group. We'll take a quick look at today's agenda, what we can expect to see. We're going to have a brief introduction to who Metrologic Group is, the company that we work for. We're going to discuss the PH20, the Renishaw PH20 and its capabilities, and specifically highlight the throughput benefits. Once we talk about that, we're going to go into a little bit of programming, how you would use the PH20 with our Metrolog X4 software. We'll do some demonstrations where we'll actually show you in real time how the Metrolog X4 software works and how the programming works. We'll talk about CMM retrofitting and what the advantage is for you when you're thinking about a retrofit versus buying a new CMM. And then we'll go into some universal programming techniques between Metrolog X4 and Silma X4, our offline programming system. We'll do some demonstrations again in real time of those features, and then we'll go into a little bit of Q&A. At the end of the presentation, we'll have time for a little bit of the Q&A, but during the presentation, if you want to ask a question, feel free to drop it into the Q&A part of the webinar. We won't get to all the questions today, but any questions we don't get to, we'd be happy to answer them and email you back after the presentation. So with all of that, let's go ahead and turn it over to Alex.
Thanks, Mike. Metrologic Group, we were in the CNC boom in Europe, and we've been working in the CMM and metrology world for about 43 years. And we do everything from CMMs, portable devices like arms and trackers, and even robotics like in the bottom right of your screen. This expertise has really bridged the gap between all kinds of different processes and help kind of expand what our customers are able to do. Our headquarters is in Milan, France, and then our U.S. headquarters is located just outside of Detroit, Michigan in Wixom. So just a little bit about what we offer. So we offer a single software, and we have different environments that you can work with. So we have Planner. So Planner is a tool where you can prepare your work ahead of time, build the GD&T on your CAD, and set up your reports, and then you can take this data and push it to Silma or Metrolog. And in Silma, we give a full cinematic model of your CMM. This lets you program offline, not take up CMM time. And when you're done with programming in Silma, you can push this to Metrolog, and Metrolog will let you measure everything online. It'll let you analyze and report. This connects to your devices. And then after that, we have our Manager Suite. And our Manager Suite is a bunch of integrated tools into Silma, Metrolog, and Planner that help you look at the OEE of your machine. You can run programs remotely. You can look at data. There's all kinds of great capabilities that are included in there with that. So with Metrolog and the Renishaw PH20, we do a direct connection to the UCC server, which is Renishaw's server system to manage this. And this 5-axis technology allows this head to move dynamically, as opposed to like a 3-axis system where that head will unlock, rotate to a specific orientation, and then lock again. Because of this, we can start seeing dramatic reductions in these cycle times, and the programming gets easier. You're not having to square as much. You can get into some very difficult locations a little bit more simply. You're not having to manage probe head angles and the orientation to the machine that get a lot of different difficulties and complexities to traditional CMM programming. And then on top of this, a great gain with the PH20 is this uses a really common probe that Renishaw uses with a lot of their other systems, and it's the TP20. So a little bit about the PH20 and kind of where those gains are is you have infinite positioning, and we index to that part. So as opposed to a traditional 3-axis CMM, where you maybe have angular increments in both the A and B axis to those, you have infinite rotation in that B axis, which is kind of our quill and that rotation of the device around, and then we have plus or minus 115 degrees to A. Anywhere in between that, you're able to get this. So this allows you to, instead of trying to come up with like interesting programming angles to make sure you're not shanking out a probe, we index perfectly to that normal on that feature, whether it's a cylinder or a plane, a slot, things like that. You're able to index directly to that. And also one of the nice, Michael, if you can hop back one. Yep. So also what's kind of nice is you're able to reduce stylus changes. When we locate into a part on there, we could have that part turned 33 1/3 degrees, and all of the motion for that once you've located into your part is relative to your part. And so you kind of get some gains where you have some freedom with your fixturing, you have some flexibility with how you orient your parts, and even have some operators that could be unruly, and the PH20 will still navigate the same around the part rather than trying to navigate absolute to the machine. So with one of the nice pieces of PH22 is we get this really great gain with calibration throughput, and there's also some gains you'll see with accuracy. So with a 3-axis CMM, like every stylus you have has to be calibrated, but all of the angles you'd like to use also have to be calibrated. This can, the second you add one angle, you've doubled the calibration time for that stylus. And so then with a PH20, every stylus you calibrate, all the angles are calibrated all in one routine. So your calibration time is really going to be determined by how many styli you have rather than how many angles you need to use. And so then once we're kind of working with that 3-axis CMM, a really complex part has more angles that need to be calibrated, and that's time your CMM is just checking itself and making sure the tip is usable and not doing work, whereas a 5-axis, that same complex part is going to have the same calibration time as your really simple part, and that's kind of a nice controllable element to your day-to-day operation of your CMM. And then another gain, one function about the 3-axis CMMs is the whole CMM frame is moving for every single point, whether it's scanning or touch trigger heads. You have to move X, Y, and Z in coordination. Maybe one of those axes is still, but with that, there's a little bit of uncertainty that's introduced into this. But again, you get with the PH20 is your scales for a lot of measurements don't have to move. So your scales are still, and we use a much smaller controllable axes with the PH20, and the head will actively flick and kind of touch onto that part. And so you get some improved accuracy, you get improved repeatability just because your frame isn't moving as much. So this is a video, this is available to you on LinkedIn. It's using a PH20 in both of these, but our top one is using our full 5-axis, and then the bottom one is simulating the use of a 3-axis head where the frame has to move. And a lot of time studies, they range like 30 to 50% reductions in cycle times on a part. A more complex part, you're going to get more gains on, and a more simple part, you might not see as dramatic of a gain. But you're increasing your machine availability to run more parts, and then because of that calibration time reduction that we discussed earlier, this is also increasing your machine availability. So that's more time to run more parts and deliver more to your customer. And then a kind of a key piece to Metrolog is our programming is really simple. It's really intuitive to get started with. We have a very CAD-driven software where we can start to simplify that feature creation. You see your part, you see your model, select that, and then visualize that measurement strategy. Because we're working in 5-axis now, we really want to understand all of the dynamics of the machine that's going to be moving. So here you can see visualized where the center of the head is going to be with that red dot, and then each line in the cone for the head touches that the styli in the center of the probe is going to travel. And that visualization really helps kind of predict what you're doing and make sure that you're getting data in the right locations. Then a nice piece too is that our programs are readable. So we have text and iconographic combination here. And even if you haven't programmed in Metrolog before, you can predict exactly what this program is going to do. So here you can see we start a working session, we pick a probe, we set up what speeds we want to use, and then we load a previous alignment. We pick that alignment, and then we go to a specific point and we start measuring features. A gain you get here is one programmer is going to be able to really easily understand what another programmer did. And the uninclined, a new programmer coming in, is going to understand a little bit more about what they're doing so they can kind of come back and learn and develop into the software. And then a nice piece too is you have this expensive machine and all these commitments that come around it, and a calibration and expensive probes and styli. And so we also have a tool called collision avoidance, where we'll account for the CAD of your part, we'll account for the simulation of your machine, what probe and styli you're doing, and even your fixturing if you want to add that. And we can automatically manage a collision avoidance and create a path that is efficient and protecting your equipment. So you can see here in the image, we actually will follow an interesting line around the part and then navigate in to measure that desired circle so we're not hitting anything. So from here, we'll move to Michael Swift, who will do a brief demonstration on how we kind of handle a lot of the programming and visualize these things.
Thanks, Alex. Yeah, this is Michael. What I'll be showing here today is, again, what Alex and Mike have been talking about. I currently have a generic CMM that I've loaded up here. Of course, we have a full library, or a very large library, of different manufacturers of frames and different volumes. So if you want something a little bit more specific to what you actually have, let us know. We probably have it in our catalog. Great. So I have the PH20 here. I have the part. I'm just going to run the program through here in the beginning. And you're going to see that with a couple clicks of the buttons in our software, I can create a collision-free program with just one of a few options that are available to the programmer, depending on their style of programming or what they're familiar with, and maybe in another software, or what they envision in their head. One thing that I'll show straight away is that we do have a clearance box or a clearance cube way of creating a collision-free program. Works in 5-axis, works with fixed head, works with the 3-axis, works with the rotary table. It just works, to be honest with you. It's very adjustable, works great. But I'm going to disable that clearance box for now, and I'm just going to show you the ability to create a collision-free program and let the software find the best path, the most efficient path from feature A to feature B, and see if the software can do it. So over here in my feature database, I have a bunch of nominal defined features ready to go, some planes, circles, and a cylinder. So what I'm going to do here now is I'm going to first turn on our collision avoidance. And you can see here I have a little toggle here, and I can tell the software how much to avoid, right? I want a 10-millimeter buffer zone. I want a 5-millimeter buffered zone, right? So we can adjust that, of course. And there's a few more options in here to enable if I wanted to. But again, I'm just going to enable the automatic avoidance. So now that is enabled and ready to go. Of course, I can change the visibility of the CMM. Maybe if I want to make it just look at the head and the part, I can do that. That doesn't affect the collision detection or the automatic avoidance at all. Whether it's being visible or hidden doesn't impact the results. So I'll just turn it back on here. But it's nice to know that you can temporarily change the visibility of the frame to get a better view. Great. So now that I have that, I'm going to come down here and tell the program where I want this line of code or lines of code of the collision-free path. So I'm going to select all the features in my database, right mouse, in this case, pulls up the contextual menu, and I'm going to hit evaluate. As soon as I do that, I'm presented with my first interaction. It's saying plane 1 is the first feature that you'd like me to measure, and you can see it shows me I'm currently using a perimeter path going around the perimeter part. I'm asking for 10 probings around that. I have my search, approach, and retract set to 2 with an additional clearance move of 10 millimeters. I can make any changes here that I want. I can change, maybe I want the head to come in from the plus X side or the minus X side. I can do whatever I want. So the software is giving me the opportunity to adjust the measurement strategy. Okay, fine. So I'm gonna accept that. And like Alex pointed out, we can see the motion of the head by the solid peach line here. So it's kind of nice to know, and it's really important to know the motion of the head as well as the motion of the stylus. So we show you all of that. So I'm going to hit OK here. And as soon as I hit OK here, the software is going to create that code, that measurement strategy. And then when it completes it, it's going to say, would you like to apply these settings, these parameters that you just did on plane 1 to all the other planes you would like to measure? And I'm going to hit yes, but I could also hit no, and I can make plane 2 have a different density, a different strategy. I can do whatever I want. So we do present you with an option there. So I'll hit OK here, and you'll see the machine simulate the motion and measure plane 1 for me. And as I mentioned, that we do provide a warning or a prompt to say, do I want to take these same parameters, this approach, search, and retract, and apply it to the next plane that you would like me to solve for? And would you like me to also do 10 probings on the surface around the perimeter? In this case, I'm just going to hit yeah. Sure, go for it. So when I hit yes, the software now is going to prompt me. It says, oh, this is the first time we're measuring a circle. So it's like the plane. It says, well, how would you like to measure that circle? What kind of strategy? What kind of density? And currently it's using a guide point. It's going to do head touches. So it's going to position the frame of the CMM, the X, Y, and Z motion is going to go to a fixed location. That's where the red dot will be. And then the actual data collection will be with the PH20 itself. So moving in the A and B axis. So the B axis will rotate around to prepare for the A axis to make contact or do the head touch. So again, I'm going to do full probings that I can zoom in here. And like Alex mentioned, I can see I'm presented with a lot of graphics that gives me a lot of information to know what the system is going to do. Whether it be the approach and retract, the direction of the probings, all that can be displayed if you wanted to. You can suppress it as well. Some people get a little overwhelmed with it, but it's really good information. So I'm going to hit OK here and say, yeah, that's fine. Go ahead and create a collision-free path and measure that circle. And again, just like the plane 1, it says, would you like me to apply those parameters to any other circles that you'd like me to solve? I'm going to hit yeah, go for it. Sure. And off it goes. You might see the software pause just for a moment when he determines that there is a collision. We get a little warning saying that he found a collision on the path or the trajectory, and he is finding the most efficient path to create a collision-free program. That's pretty much what that does. And so now I'm presented with the first cylinder that it's in my program that I need to create a measurement strategy. And you can see here, like I mentioned, that there is a little display message that currently there's a collision detected on the path from my last feature to the feature that I want to measure next. And if I zoom in here, I can see the gray dashed line of where the probe currently is, last known location, into where I'm asking the probe to go to with this measurement strategy of the cylinder. And you see it's clipping through the part. So great, found a collision, and I can solve for it manually, or I can let the software solve for it. But before I solve for it, what I like to demonstrate here is that I may want to change some of the parameters of how we are measuring the cylinder, right? Maybe I want to take 4 probings instead of 6 around. I could do that. I could change the start and end angle. I can measure 180 degrees, 92 degrees. I can, of course, do any of that. I also might want to adjust the depth of the feature measurement. So maybe I want to start 1.1 millimeter from the top perpendicular surface, and then also on my second band, go 6.9 millimeters from the top surface. Maybe I'll shorten that up a little bit to 5 millimeters. Sure, I can do that. And there's a few more options. I also have the option down here that I like to show is this is where we can control the 5-axis parameters inside the software. So currently it's set to automatic, and automatic to us is the most efficient way to collect the data. using the hardware that we have in case the PH20 here, since we have the PH20 here, it's going to try to do head touches if it can. It's the most efficient, most accurate way to use the hardware. So I'm going to come down here. And one thing I would like to adjust is that I see that I have a lot of frame motion, and that's indicated by the peach lines here. That in this scenario with this feature, the frame has to move around in addition to the AB for accessibility, so I don't shank out, so I don't crash. And though 30 degrees, which we see in this parameter here, is fine, I can actually change it to 40 degrees if I wanted. And you can see here, we allow you to do that, but we can also see that we have a different indication of the colors saying, yeah, you're using the hardware in kind of the, you're approaching the unsafe zone, or the area that you may not be collecting the best possible data within the manufacturer's stated requirements. So we're going to show you that graphically. In this case, I'm just going to move it down to 10, and you can see by changing the elevation angle to 10, I'm going to have less frame motion. The XYZ is going to move less, therefore a better chance of measuring this more accurately or repeatedly. Okay, great. So I'm going to hit OK here. I have this new strategy. I still have a collision on the path, but I'm going to now accept this strategy, and I'm hoping that the software will solve for a collision-free path. And we'll hit continue. It's processing, and it found a solution. There's my collision-free path. Again, another pause to go to the other side of the part. Give it a moment. Calculating. And rinse and repeat. So the program is now complete. I have created a collision-free program using the collision avoidance options in our software, and I can highlight the block of code and show you all the paths, or I can look at one of the features independently. So, but now I don't have to worry about go-tos. It's done. It's solved. It's collision-free. I can deploy it on the CMM and have high confidence that the program will run collision-free. A couple other things we like to point out while we're here is that what if, for example, we wanted to change a measurement strategy for one of the features? Let's say in this case, if I click on this feature, I know this is circle 15. I can come to circle 15 here in my program, and by double left mousing on it, I go into the edit mode, and I'm presented with the same graphic that I've seen previously. In this case, I want to change the density, the probing points from 12. Let me zoom in here a little bit to 12. So there's your 12. You see it dynamically updated. I hit OK, done. That's how you edit in our software. I like to say it's fairly quick. It's fairly easy once we show you how to do it. Yeah, and we can change any of the parameters, the approach, the retract, the spacing. We can, of course, change all those other parameters just as easily as I changing the density here. So that's kind of nice. Another thing that I like to show is how to edit or create a go-to, a clearance move. So I currently just position to the first go-to here. There's multiple ways of doing it. This is a common one that we see a lot of people like using, is by, again, editing the line of code, in this case, the go-to, and I can see it's a 5-axis. We're presented with these handles, or what we call manipulators, where I can graphically, with my mouse, grab the axis of interest that I want, and I can drag the probe. And it will move or update the position based upon where I drag it. So I can change this preview here, so I can see this is where it currently is. And if I enter these values, or if I drag it, I can see the simulation, the motion of the probe. It's kind of nice. It's a nice tool if you don't want to type in a precise number. We also have the ability to adjust the A and B axis as well with the holding of the shift key on the keyboard. You can see we're presented now with two different handles. You see a red and a blue. So the red, you can see it here. This would be adjusting the head this way or this way. Kind of nice. And again, the blue is the same thing. We can rotate around. So we have the ability to graphically drag and drop. So if you don't know what A45 is, B90, doesn't matter. Just graphically grab the angle, position the probe so it looks good, and hit OK. Pretty straightforward there. And what I say, and again, the preview works for us as well. So we can do combo moves, of course, since it's 5-axis, moving the 3 axes of the frame, as well as AB simultaneously. So a true 5-axis motion. So editing or creating go-tos is, we like to think it's, again, with a little bit of training and familiarization with the windows, you can create 5-axis moves easily. That concludes the PH20 automatic voidance demonstration.
Thanks, Michael. So just showing that capability is great. Collecting that data easily is really great. A really important piece to this is also being able to express that data. We get all these really nice CMMs, we get all this great hardware because we find that the data they create is really valuable, and that's kind of what we start getting out of our reporting. So a really easy piece is just the traditional tabled report. Here you can see that we have a pretty straightforward report. It's telling us what the feature is, it's telling us where it is, what our tolerances are, our nominals and deviations, and then we have some visual cues to quickly be able to kind of rip through this report. So we see that this report's good, and this is helping us like have efficient translation of these reports. Another piece that we have is that we can do views and stickers, and so these are a really great tool to tell people where you took that data. A lot of times the CMM programmer is going to translate, hey, I took the data here, and then the machinist or the quality engineer or the manufacturing engineer isn't necessarily going to translate perfectly where things are. The stickers are a really great tool to where if you have like unregulated nomenclature or you have just more visual people on your team, you can start translating really efficiently what data is where and what the trends in this data is looking like. And then a really great piece of our software is our GD&T interpretation. So this is an included tool is our detail viewer, and so we'll interpret the GD&T that you give us, and we'll help create a visual tool to where we're showing you your tolerance zones, where your gauge alignment based off of your datums is built, and translate some of that really complex and difficult GD&T to help everyone in your help all your stakeholders understand the value of the data, but also understand what's going on with their part. The detail viewer is particularly valuable because if we look at something like here, like bidirectional position, we can give these two values, but if someone isn't perfectly familiar with that, they might not be able to translate in their mind what's going here. But thankfully, not everybody on your team has to be a GD&T pro. Instead, they just have to understand what their part is and what the part is doing. And now with this detailed view, you're getting a more meaningful translation to those team members and those stakeholders. So Silma X4, just to emphasize again, this is a different interface to the same software. So this is something where we'll simulate your CMM, just like Michael was doing earlier. It uses all the same files as Metrolog X4. And this will let you do this simulation of this machine, and you can really program from anywhere. A lot of our AEs have done contract programming, and we'll pull in a customer's machine environment, and we can predictably program everything for their parts. And so when you're using Silma, you're not using the machine, you're not taking up that desk, and so your machine can keep running parts instead of you sitting there with a part, programming feature by feature, making sure everything's collision-free. Here you could be at a desk, you could be at home, you could have a third-party programming here, and your machine is running parts and getting throughput. And then another really nice piece is Michael had used the collision detection tool, and that collision avoidance will indicate, like that image on the right will indicate when you're hitting that. And this is really preventing like downtime and damage to your parts. I think everybody is at some point or another as a CMM programmer, you've broken a probe, you've broken a stylus, you've smashed a head straight into the table. Maybe not that last one, but I've done it. And when this happens, there's a lot of downtime that happens. You have to restart the machine. You might need to change probes out and then recalibrate that new stylus. You're going to need to calibrate that stylus. So that's downtime that's not running parts, and you can avoid damage to those components. The TP20s, all the other sensors are not necessarily negligible costs. And ultimately, you're increasing your machine uptime because all of this is simulated ahead of time. We know it's reliable. We can send it out there. We know that we're going to run a safe path and we're going to run an efficient path ahead of time. So we're going to have Michael do another demonstration, kind of talk about a little bit of what we can do with reporting, how we can look at detailed views and GD&T. Michael, take it away.
Great. Thanks, Alex. Yeah, so I have another session of our software running. In this case, it's Metrolog. It could be Silma. And what I have here is a finished part that has been inspected with a few views saved. And I can also show you a simple tabled report as well as a graphical report as well, or combinations therein. So what I'm showing you here, the first one that I'm going to point out is that a positional evaluation, but this positional evaluation is a projected and offset. So which is kind of nice to be able to see that graphically. And I'm seeing that graphically. So the green cylindrical surface or cylinder that I see here is the tolerance zone, 2.2, in this case millimeters, projected 35 millimeters, offset 10 millimeters from the surface. So if the customer has a projected tolerance zone with or without an offset, we can show you that. And the green, it's green because it's in tolerance. So we can look at the features, and we have them exaggerated here, but this is the top or bottom entrance or exit, whatever verbiage you like to use, but of the two extreme points of the cylinder. So we can show that with the little whisker. We also connect the two little whiskers with a dashed line so that you can see the orientation of it as well as the offset or the bias. So you can see here that the axis of the measured feature, which in this case, to be very clear, is the cylinder down here. So by highlighting it, you can see these little spheres or orbs with the probing direction. Those are the actual probing. So this part was measured on this feature down here. Then we created the positional evaluation that is projected and offset. So you can see where the probings are, see where the tolerance zone is, and then you can start seeing the information about the feature. So we can see that we have a bias in the X direction, so it's a little bit offset, and it has a little bit of lean to it in the ZX plane. Cool, right on. So that can be helpful information. Again, graphically, we're showing that, but then of course we can attach numerical values to that so that you can provide that to the manufacturing team or to your customer. The metrology team can provide it to their customers to make a better part. We can also look at it in a different orientation here. And in this orientation here, you can see that it's a little bit, it also has a bias or a shift offset in the Y direction, but it's a little bit more vertical in the YZ plane. So again, very graphical. Or can be very graphical if you choose to see it. So yes, we provide a numerical number. We can provide state of tolerance, the tendency, that all the numerical data that you would expect and would want to see. But we also support it very well, or we think we support it very well, actually, in our detail view, specifically with the 3D graphics. So that's just one example. Again, we could look at a tolerance zone. This is another positional evaluation. But what we see here is we see two cylindrical tolerance zones. This is kind of nice to see that if the feature itself has a material modifier, in this case it has a MMC modifier, we can show that modifier being applied so that the tolerance zone of 1.5 is shown in gray. Then the actually measured feature, when we calculate the material condition, we can apply the bonus and show that tolerance zone, which is in green. So it's kind of nice. And again, you can see here with the gray dash line where that line falls in between the tolerance zone. So it's kind of, again, very, very graphical, showing you the material modified tolerance zone as well. So we find a lot of customers like to see the information that way. This one is, I always like to show this one because distance is always fun to report, in my personal opinion. This one, you can see that we're reporting distance, but 3 values. We see the D value, right? And you can see that that's the average distance between the two using the envelope rule. But we're also displaying the D max and D min. So you have the numbers, which are great, but we also show it graphically, and you can see, and these are auto labeled stickers. So when you want to get detailed information about a distance, you're going to get that. So you can see all the probings on this surface, grain intolerance, a couple were red, and then the same on the opposing surface. So you can now look at the minimum distance between the probings as well as the maximum. So you can make a more educated decision if there's a goes into that area. But so it's nice to see it graphically. I think it's really neat to see. Another one, of course, we do. So that's distance. We do position. We do a lot of them, to be honest with you. So this is another example. This is parallelism. This is nice to see here that with the parallelism, you see the two parallel planes around the nominal location of the plane. They're currently green because the part's in tolerance. If it was out of tolerance, the planes would show red. So if I look at it this view, you can see the trend of all the probings on the surface, and they're well within the tolerance zone. And we can apply stickers of the minimum point, the maximum point, right? We're very good, and we give you all the control to create all the information in the sticker that you want to see, or not create a sticker or reduce the amount of information. So if it's overwhelming to you or your customer. What's interesting about this one, if I were to rotate the view a little bit and look at the data in this orientation, which is kind of fun, you can see that the parallelism has a trend. So we can see graphically where this surface relative to its datum, which is down below down here, it has a little tilt to it. So not only is it offset, but it has a pattern, has a shift, has a tilt to it. So it's kind of nice to see. I mean, so if you could create this view in just a matter of moments and put this in your report as supplemental information to provide some sort of graphical input, it just generally saves time. One little thing to point about at the bottom as well is that this is using the surface on the bottom. It's actually calculating it correctly, or finding the extreme points on that planar surface. So we like to say that we calculate and demonstrate that we can do the calculation per the standard, whether it be the ISO or the ASME standard, correctly. So we have several different examples here. A couple other ones that I'll point out is ran out of a plane. Again, I'm measuring this planar surface. I want to look at it. We have the ability you can see here with the probings, but then we can create a curve or a spline and connect all this of those probings, so you can graphically see the waviness of that surface. So with the whisker and the connected line, kind of nice. It's a nice graphical view, in my opinion. And of course, we can do the axial one as well. Same idea, just the features, right? We see the lobing of the part in this example here. So those are just a couple of examples that we can show. We have plenty more, so if you're interested, just let the team know, and I'm sure that they would follow up with you. Let's see. I think that concludes the GD&T detailed view side of the presentation.
Great, thanks, Michael. So kind of when we start looking at like a tool like the PH20 and Metrolog, one of the questions is like, how can I get this? So you can purchase a new CMM and get a PH20 put onto that based on whoever your supplier is, or you can have an existing CMM that might be maxed out on throughput, kind of topped out, and we could actually just retrofit it. We could take the original frame, even use the original scales if we can, and we'll replace the existing controller with a Renishaw UCC controller and give the machine a whole new calibration. And this can give like a really good frame. You're not throwing it to waste. You're not having to go like upset it for a whole new CMM or add that different CMM. And this is something that we can do, or one of our partners, one of our Metrologic partners can also perform. And some of the value you get with retrofitting a CMM, you're not committing as much capital when you go to retrofit the CMM. So you can increase that throughput, and you're not adding extra operators. You don't have to increase your utilities utilization. You don't have to even have a separate programmer, especially if you buy maybe a different brand and it comes with another software. And you don't have to commit more floor space to another machine. And then lastly, you're also not calibrating another machine. So that PH20 is really integrating into your set costs. You pay for that one time, and then all of your pre-existing costs don't change. And so you can see over the years, you really do see a pretty large savings in that. And then a key thing about Metrolog and Silma is we don't just program the PH20, we program all kinds of CMMs, whether it's 5-axis PH20s and Revos, or 3-axis horizontal machines, large gantries, small bridges. And with this, we can actually start sharing programs between these machines with some semantic changes and differences to these. So this lets us inspect using any type of measurement hardware and limiting the amount of different software we have to know. And this is also spanned out to portable devices. So if you have like a 3D scanner, you have a portable arm, you have a laser tracker, or maybe a laser radar that you're using, all of this, we can bridge the gap of correlation between these different devices. And then a key thing we do is we have universal connections, and we like to talk directly in that machine's language instead of getting maybe an I++ server. We like to talk directly to that controller in that controller's language to get the absolute best performance out of that machine. And this is spanning across really all these manufacturers and even more than these. So even if you have an old machine that's using an old controller, chances are we might have a connection for it, and we can connect and run that.
Okay, we're getting near the end of the webinar now, but I'd like to take the opportunity to just go through and review some of the questions that we have. So we'll do a little Q&A here with Alex and Michael, and we'll start with the first one here that I've got. It says, what does a retrofit require? How much is a retrofit? Alex, you want to go ahead and take that?
Yeah. So a retrofit normally can be around about $70,000. But costs can be lower or higher depending on the machine if you need to replace scales. And we would just want to look at the machine, see what condition it's in, see what kind of parts and pieces that are required for it, and buy Metrolog with it.
Perfect. Let's take a look at another question here. So it says, does Metrolog require a UCC offline for simulation? Michael, you want to tackle that one?
Sure, Mike, thanks. Yeah, the quick answer is no, it does not. Our offline software, Silma, does not require any additional software, specifically the UCC server provided by Renishaw. It's a standalone.
Okay, perfect, thanks. Next question, how do I switch to Metrolog? Alex, you want to try that?
Yeah, with a lot of different companies, we do this all the time, and we can help you transition from your existing software. The first step is buy Metrolog and get trained up on it, and then we're able to assist you with transitioning from your existing software, train you in how to use Metrolog and the best practices, and really help you start getting those gains on your CMM.
Okay. This next one is more of an engineering question. So it says, can I mirror a program? Michael, you want to do that one?
Sure. Thanks, Mike. Yeah, we get that quite frequently. The answer, again, very short, yes. We can mirror an entire program. We have the ability to mirror a block or a selection of code. And we also have the ability to mirror a single feature or a single point inside of a feature. So the answer is yes, we do.
Okay, great. Next question, and this one is about using the Metrolog software on different brands of machines. So it says, can I run my Hexagon and my Zeiss machines with Metrolog? Alex, you want to take that one?
Yeah, we directly connect to those controllers. They're depending on the devices you want to use, there may be some better strategies than others, but yeah, we can connect to really any machine that's out on the market right now.
Okay.
Or nearly, rather.
Okay. Next one says, are Silma and Metrolog different softwares? I think, Alex, you talked a little bit about that already.
Yeah. So experientially, Silma and Metrolog, the only difference you're going to see is the icon in the top left corner is going to be yellow or red. They are the same software in that you're using the same files, you're programming in the same methods. Silma just has some tools that Metrolog does not have, and then Metrolog has the ability to connect to machines that Silma doesn't have.
Okay, very good. This is a question about GD&T. So it says, I use another software that doesn't have circular runout callout. Does Metrolog have this? Michael?
Yeah, oh, that's good timing. Yes, we do. I'm sorry, I could show it again in our detailed view here. We do express out the runout again, whether it be a planar or this is total runout, of course. So I can do again. You see the runout call out here on the planar surface, as well as a diametric surface, a cylinder in this case, and of course we can do the total runout as well. And this one just so happens to be on a cone. So the short answer is yes.
Great. Well, thanks for showing us that. And then last question we have time for today says, how does Metrolog handle scanning arm inspections? Alex, you want to take that one?
Yeah, Metrolog has a lot of tools for scanning arm applications. We haven't really gotten to go into these here, but we'll directly connect to that. We'll directly pull the point cloud into the software. We even have some tools that can help you automatically orient the view of the part to the scanner. That may be a good topic to touch base with after the webinar.
Oh, very good. Well, I'd like to take the opportunity to thank both Alex and Michael for the great presentation material today and being able to put together this webinar for us. As you can see, there was a lot of great information here, and I think we just kind of touched the tip of the iceberg and gave you a flavor for how Metrolog works with 5-axis and how easy it is to program PH20 and other examples of 5-axis machines. So we would love to get more of your questions. We'd love to talk more with you about our suite of software products. Feel free to connect with us. We have a great website. The website address is listed there, www.metrologic.group. You can also find us on LinkedIn, on Instagram, and YouTube, where we have a whole series of great videos that go through and show you real practical examples and practical demonstrations. We encourage you to reach out and connect with us via those ways, and we'd love to talk to you again. So thank you so much for joining us today, and we will talk to you again soon.